Cities across the UK face growing pressure to manage infrastructure under stress. Floods, delays, large events, and technical disruptions ripple across multiple sectors. Our team set out to explore how a digital twin of the railway could help predict and mitigate these impacts on the rail network. Using SAS Viya, we envision an intelligent system that fuses live rail, passenger, and weather data with predictive and optimization models to forecast disruptions, reroute journeys, and support data-driven decisions for operators and planners. This proof of concept shows how rail data, enriched with predictive modeling and visualized using SAS Visual Analytics, can give automated outcomes and valuable insights to Southwestern Railway's network operations. We focused on Southwest Rail region, integrating open datasets on train schedules, passenger loadings, and rail network delay attributions. The power of SAS Viya's CAS-enabled architecture enabled us to generate value from these large historic datasets quickly. And the flexibility of the Model Studio allowed our data scientists to try multiple modeling methodologies at once.
As part of the data exploration phase, we searched for data concerning disruptions to rail travel. So data on station codes, delays, as well as data on possible reasons for delays, such as flood data. We got this data from a variety of sources, such as Network Rail, and explored national data, as well as data specific to our chosen region.
We developed 3 predictive models in SAS Model Studio. The first model predicts the average train load on departure, essentially how full a train is likely to be. We initially started off experimenting with various machine learning models and data processing nodes available in SAS Model Studio. In this case, random forest regression model from Pipeline 2 was classed as the champion model. It achieved an R-squared of around 0.8 on the training set and 0.77 on the test set, meaning the model explains about 80% of the variation in passenger load. This means the model can reliably anticipate passenger volumes ahead of time. The second model predicts whether a train will be delayed or cancelled. This classification model is also built using random forest, which has performed really well in terms of classifying delays and cancellations of trains with 90% accuracy and F1 score of 0.94, accurately distinguishing between delays and cancellations with minimal misclassifications. The model also generates a classification score which can be used to add a value to the probability of a train being delayed or cancelled, providing more certainty to rail operators in terms of impact decisioning. This can allow rail operators early detection of high-risk journeys that may be disrupted. The third model also uses a random forest regression and forecasts the train delay time, with the key features being service type, route section, and operator. With an R-square of 0.75, it reflects that about 75% of the variation in delay is explained by the model, which is strong performance for real-world problems like transport delays. The average errors measured across mean absolute error and root mean squared error were 3.8 and 9 minutes respectively, suggesting the model performs reasonably well for most observations. These models create a foundation of intelligent decisioning, which allow access to real-time predictive insights for rail operators and passengers, giving information on service demand, disruption likelihood, and expected recovery times. We then deployed these models using Model Manager, so we could use their model cards in the intelligent decisioning workflow. We built a decision flow that monitors predicted delays. We first used the deployed model to predict delays and cancellations, and then developed 2 rule sets to define how decisions should be made in each case. If the model predicts that a train will be cancelled, it is passed to the cancellation rule set, where a cancellation flag is raised and a message is generated to update operators or passengers about the cancellation, including the reason. For trains predicted to be delayed, the output is passed to a different rule set that checks the duration of the delay to determine whether it is minor or significant. The rule set verifies whether the delay exceeds 15 minutes or not. If the delay is less than 15 minutes, it is considered to be a short delay, and a message is generated to update the delay information. If the delay exceeds 15 minutes, a different message is triggered, updating the exact delay time. At this point, the shortest path analysis node can be integrated into the workflow, which could automatically recommend alternative routes using our shortest path model. This serves as a proof of concept demonstrating how predictive analytics and decision flows can help keep passengers moving even under disruptive conditions.
So this is the dashboard for South Western Railway users. They can see all of the trains scheduled on South Western Railway's network and find out information about their route, their journey, including the number of passengers and the number of cars and arrivals and departures for each location en route. This first page allows users to put in any two stations in the network. These two filters then come into the route selector so that only schedules from both lists arrive on the selected route. Then we can pick a particular route, expand our schedule to find out all the schedules on a Wednesday or any other day of the week and investigate that further. This will highlight that particular route here on the route map and give all of the details for each location, including the car count on the train and the average train load between stations. The second page is the delay page. First, on the right hand side, you'll see a stacking container, and the first is the number of delayed incidents that have happened along these routes. We also have average time delayed and the total time delayed for these routes. When we find a schedule key of interest, we can then input this into our schedule key search here. And once we've selected this, we can see a log of the delay incidents over the last 3 months, which includes the amount of time on each delay event. We also have two key values which state the total time lost on this route over the last 3 months and the average number of minutes delayed. And finally, we have the route details such as the origin, destination, the time at each location, both arrival and departure, and the average train load between each station. And these will allow users to note why certain trains are consistently delayed. Next, we have the cancellation overview page. On the right-hand side, we have once again a stacking container with 3 bar charts with a top 10 ranking of the most number of cancelled trains on the route, or the trains that have the highest average time delayed when cancelled, or the trains which have the most time delayed from cancellations. We also have a visual of the route map showing the direction of the train and a red, amber, green to show what it's at capacity-wise.
One of the key features we wanted to implement was the ability to reroute trains in the case of events like flooding, blocking of route. To achieve this, we needed the ability to find the shortest path through the rail network. This was made possible through data obtained from the Rail Data Marketplace. We then used the link node model to give us information about the location of the stations and the associated track center lines. Before analyzing the rail network, we had to prepare the data. The pre-processing was carried out in Python, mainly using GeoPandas to clean the data and NetworkX to build and store the graph. The shapefiles of the rail network use a proprietary asset ID to identify the stations. So for our purposes, we needed to match each station with a station name. This was done through spatial joins with GeoPandas. Using NetworkX, we then built the graph with stations as nodes and track lines as edges, preserving their length for travel time calculations. We were then able to query the graph during analysis, for example to find the shortest journey between 2 stations.
We use SAS Viya's geospatial analytical capabilities to visualize the train lines and their stations around the UK. We then did some analysis to see how floods could be impacting those train lines. So you can see we've got all of the train lines in the UK on the left, and then we've got all of the train lines and all of their stations on the right. And then we were also able to do some filtering by track section as well, which you can see in the middle. And we then used a publicly available flood API, which will give you a flood warning and then show you the region that will be impacted. So you can see all of the flood regions in the Devon and Cornwall area in this bigger picture on the left. And then we've then used some geospatial analytics using the proc geinside function to see which of these train lines then fall within those flood regions. We've then done some filtering to say which floods are impacting a train line, and those are highlighted in red. We then combined our flood region mapping with the train tracks as well, and we're able to produce a custom geoline graph which shows the sections of track that are impacted by flooding, and those are highlighted in red.
There are many more datasets gathered for this project that could be of use. Future work will include integrating weather data and flood maps for better visibility of oncoming disruptions, events data for predicting higher demand, and public accessibility information for improved travel assistance during disruptions. Eventually, this digital twin could evolve into a powerful decision support system for operators and policymakers. This is just the beginning of our vision for a smarter, more resilient public infrastructure powered by SAS Viya.